I will be explaining the calculations problems of Ben Fuchs. For this first calculation problem, I would solve it the same way as Ben, so I will explain the problem with his solution. This calculation problem covers topics 1, 3, and 4, which includes hydrostatics, Bernoulli, and momentum balance. Hydrostatics was first used to find the pressure at the bottom of the tank, as depicted in Part A. The properties used were found in handouts 1 and 4 for the density of water at the specified temperature of 10 degrees Celsius and the atmospheric pressure. To use the Bernoulli equation in Part B, the water was assumed to be at steady state, incompressible, no work and no friction, and V1 was considered negligible. The exit velocity of the water out of the nozzle could then be calculated using the Bernoulli equation as shown in Part B. In Part C, the water was assumed to have no y-directed component, exiting, as the water was assumed to exit in the x direction only. To find the maximum mass of the ball, a momentum balance was used, as well as the continuity equation and the Bernoulli equation. I would do this problem the same way that Ben did this problem, so I will show his work as I explain this problem. This problem will cover topic 2, which is buoyancy. In this problem, the buoyancy equation and Archimedes' law are both used. It is assumed that water has a constant density and that there is constant gravitational acceleration. The density of water was found in handout 4. The buoyant force acting on the board was found because the buoyant force was equal to the weight of the floating object. In Part B, Archimedes' law says that for a floating body, the weight of the object equals the weight of the displaced fluid. So, to find the maximum amount of gear that someone on the paddleboard could carry, this was applied, using the given dimensions of the board to find the volume. For this problem, I will explain through the extended Bernoulli equation to cover topic 3. I would do this calculation problem the same way that Ben did, so I will show his work as I explain. The extended Bernoulli equation was used to find the maximum difference in height without cavitation. The properties used were found in handouts 1, 2, 3, and 4, and the fluid was assumed to be incompressible and that V1 was much smaller than V2. After determining the flow in the pipe to be turbulent by calculating the Reynolds number, the fanning friction factor was used, and then the friction loss of the pipe was calculated. Then, the friction loss from the porous media was also calculated using the turbulent portion of the ergon equation, due to finding the Reynolds number for the flow through porous media to be turbulent. The extended Bernoulli equation was then used to find the maximum height difference before cavitation.